Hi students. So today I will start Fortran tutorial lecture 13 and we are going to discuss one more topic on numerical integration, which is the Gauss-Legendre quadrature. I am Dr. Ganguly. Now of course we know that as far as the problem of finding a definite integral is concerned, you need to find the integral fx dx from a to b. We can look at this as finding the cross section of this shaded region here, which is between the curve f of x, the line x is a, and the line x is b. And we have seen that the uniform grid methods which are there, such as the trapezoidal rule, the Simpson rule, these essentially split this domain between x is a to x is b in a uniform grid, and then it calculates all the different function values at those points, and then you find the integral. Now those methods are very useful in many situations where you may actually have data where y is a function of x and you have the data, let us say, at a uniform grid. In that case, of course, you have to use the trapezoidal rule or one of the Simpson's rule. Remember, that is the 1/3 rule and that is the 3/8 rule, which I have discussed in the previous two lectures. But today we are going to discuss a different method, which is the Gauss-Legendre endpoint rule. And this method basically says that if you have the integral from -1 to 1 f of x dx, I can approximate this as summation I is 1 to n wi fxi, where wi are the weights and these xi values are actually roots of Legendre polynomials. Now in this particular method, what happens is that you use a non-uniform grid. So these points x of I, they are not uniformly spaced between a and b. And these points are actually optimally selected. There are several different methods out there. The use of Legendre polynomials is only one method. There are different methods out there, but this is probably the most popular method. So we have to essentially use this formula, but of course you realize there is one important step which we need to make. And that step is that most integrals are given in the form f of y dy integrated from a to b. But as far as the Gauss rule is concerned, it is expressed in the form -1 to 1 f of x dx is this summation here. Now I have used this variable y here just to differentiate between this integral here, which is going from a to b, and this integral here, which is going from -1 to 1. Now this is not a problem because we can actually find a relationship between y and x, and then we can express any integral of this form a to b fy dy in this form here. So let's try to do that. So essentially I will need to transform the variable. So I assume a linear transformation here in the form y is mx plus c. I want to go from this definite integral in red to this definite integral in blue. Now what I do is I substitute the situation. For example, you can see that when x is 1, y is b, and also that when x is -1, y is a. So I put these values in the straight line here, and after I solve these two equations for a and b, I can calculate the value of c and m as given here. So in this case, what I did, I add these two equations. So I get this equation here, a plus b is 2c. And when I subtract these two equations, I get b minus a is 2m. And so I get the values of c and m. Now I put these values back in y, and then I get y is b minus a into x, b minus a by 2 into x, plus a plus b by 2. So essentially I can make this substitution now. So that's the transformation. We have the transformation of y in terms of x, and I can immediately differentiate it and get dy as b minus a by 2 into dx. Now I can take this integral and I can write it as follows. So all that I have done is I am using the fact that I have this b minus a by 2 dx coming from dy here, and then I have this function value here where I have simply substituted y as b minus a by 2x plus a plus b by 2. So that's what's given here. So essentially if I have some definite integral in the form a to b fy dy, I can write it in this form where it is in the variable x and it goes from -1 to 1. So now let us try to write the Gauss-Legendre rule. So I have written it here and you can see that I can now write this definite integral in this manner here. So all I have done is I have substituted this bound here -1 to 1 the integral sign by the summation sign, and I go I is 1 to n for the endpoint rule. I have the weights and I have the function value at each of those points which correspond to x of I. Now for each Gauss rule we are going to get wi and xi from some database out there. There is a lot of literature on Google where you can find these values, but if you are interested in the derivation, you have to look at the theory. There are again many lectures on that in YouTube as well as on Google where you can get the derivation of wi and xi. So today I'm going to look at two cases. I'm going to look at case involving n is 3 and n is 7. But first there's an important result which you need to keep in mind, that this Gauss endpoint rule will give the exact result for polynomials of degree 2n minus 1 or less. So for example, if I use n is 3, I will get exact results for polynomials of degree 5 or less. So for example, if I have a quartic polynomial, cubic, quadratic, linear, and a fifth degree polynomial, they are all going to work very well if I have n is 3. But if I use n is 7, I can go all the way up to polynomials of degree 13. So that's going to cover 13 and below. So of course, the choice of which rule you use depends on the kind of polynomial, kind of function you have. In general, if it's more, it's going to be better. But again, there is going to be slight increase in computational cost. So I'm going to look at these two situations. N is 3 is going to be pretty good for many polynomials which are maybe quadratic, cubic, quartic, and so on. And n is 7 will of course take care of most polynomials because 13 is quite a high degree. So let us start with the 3-point rule. In the 3-point rule, I will go from I is 1 to n will be 3. And these are the 3 weights here, and these are the 3 points here. So you can see the point is 0, minus 0.77, and 0.77, and the weights are 0.88, 0.55, and 0.55 expressed to more decimal places. So then we can express the Gauss 3-point rule as follows. I am going from I is 1 to 3. There are 3 weights, there are 3 points, and again we can write this in this form here. So if I have the integral a to b fy dy, I can write it as b minus a by 2 into this summation. So this form is something which I can write a computer code for. So of course I need to find some function, and then we are going to write a Fortran code for this particular problem. So we are going to use the function which we have used several times before as far as the numerical integration is concerned, that 0 to pi by 2 cos x by 4 plus sin x into 1 plus sin x dx. And this has a closed form solution 1 by 3, 3 log 2 minus log 5. And remember that you can find this closed form solution very simply. If you want a check, in my math tutorial 6 in the Math Mania playlist, this is question number 6, so you can look at that. Of course, you can realize that if you substitute 1 plus sin x is t, you can solve this definite integral. Now the numerical value is 0.15666, so we'll try to get this value. So just as a check, I have plotted this function. So this function is quite a simple type of function. You can see here, at least in the domain I have considered between 0 to pi by 2, and Wolfram gives me the solution to be 0.15667. Now this is of course the function here. Let us now proceed with the Gauss quadrature. Immediately you realize that a is going to be 0, that's the bound here, and b is going to be pi by 2, that's the bound here for the definite integral. So now I am going to calculate this integral I using a Fortran program. So I start with the main program. For n is 3, I'm going to write the main program as follows. I write pi as arc cos -1, a is 0, b is pi by 2. I put in the value of the exact solution. Remember that was 1/3, 3 log 2 minus log 5, which is written out here. A log is the Fortran function for natural log. and then I call this function Gauss3 and I feed it a and b, which are the bounds as far as this definite integral is concerned. In this problem it's 0 to pi by 2, and this Gauss3 is going to give me back a number which I'm going to call tint, and then I'm going to print this Gaussian quadrature estimate and the exact solution, and we are going to compare these two values. So of course I'm going to need a function to calculate the math function. So I have cos x divided by 4 plus sin x into 1 plus sin x. I simply write this 3-line function, and this is going to help me find f. Now I would need to get in the weight somehow and the point. So I create a subroutine. I call it WTS PTS, so weights and points. And what this gives me is W1, W2, W3, X1, X2, X3. So this is a simple case with n is 3. So I'm using scalars here. When I do the program for n is 7, I'm going to use the vectors, but let's right now just write these out. So I have simply copied and pasted these from the values I have shown you before in the table. So these are the values here, and you can see these are the values here. So there are 3 weights W1, W2, W3, and 3 points X1, X2, and X3. Now I need to write the Gauss function. This is a 3-point Gauss rule function. So I call the function as Gauss3. The inputs are a, b. I call the weight function here, which I have shown in red, and the weight function, or rather subroutine, will give me W1, W2, W3, X1, X2, X3. Then I'm going to define some variables. For example, I have this b minus a by 2 coming in twice. So I call it bma is b minus a by 2. I have b plus a by 2 here. I call it bpa. And then I calculate this value inside the function here. So this value is going to be bma into x1 plus bpa. And then there are going to be 2 more values. So all these are going to correspond to the 3 different terms in the summation. So f1 is the first term when I is 1, f2 is the second term when I is 2, and f3 is the third term when I is 3. And then I calculate the value of Gauss3 as this BMA, which is b minus a by 2 into w1 f1 plus w2 f2 plus w3 f3, which is essentially the summation here. So let's now check out how this does. Let's take all this and put it in the compiler. So here I have used the onecompiler.com online system, which actually calculates the Fortran output. So I put all this stuff here. I have basically copied and pasted whatever I wrote into this compiler. So you can see there is a main program here. There is the function Gauss3 here. There is a subroutine to calculate the weights and points. And there is a function to calculate the math function f of x. And at the end of the day, when I run this program, I get these as the output. And you can see with only 3 points, the Gauss quadrature rule calculates the integral pretty well. I get an estimate as 0.15665, which is good enough for most people, certainly good enough for most government work. Now remember that as far as polynomials are concerned, I should get exact result for polynomials up to degree 2n minus 1 or less with this rule. So this is going to be 5 or less. So I essentially create a problem 0 to 1 6x5, which is going to give me 6x6 by 6, 0 to 1, which is going to give me 1. So this nice test function should output 1 to me if I use the Gauss quadrature rule. Let's see if it does. So essentially I have changed the function here. You can see here the function is 6 into x to the power 5. Remember, power is essentially created by this exponentiation. So double star stands for power. And then I have a is 0, b is 1. I run this code. And when I run this code, I get a pretty close number as far as 1 is concerned. The exact solution is of course 1. I have hard coded it in that program. And here I get Gauss3 is almost 1. So it's pretty good as far as most things are concerned. Now remember that there are some numerical issues which take place whenever you actually run a program. These have to do with the fact that as far as computers are concerned, here I am simply using 8 points in terms of the decimal places, and so it's working with that, and so there is always round off truncation and so on taking place here. So actually for most work you may be better off with using the Gauss 7-point rule and using actually many more decimal places. So here I have considered a situation where I have access to many more decimal places, I think 16 here, and I'm going to write the code with double precision math. Now remember that in this case what's going to happen is you can get these numbers from many places in the internet out there. Make sure you check them slightly because sometimes there may be mistakes, but I think most of the people have been simply copying and pasting things. So that's what I have also done here. I will put the link to this particular web page, which is very useful, on the description box. It essentially gives you all the weights and points from ns2 to 1 to ns64. If you can believe it, there is a 64 point Gauss rule also. You may want to use that if you want to actually solve problem with very high degrees of polynomial. Now there are some methods such as p version, FEM and so on where you may actually use very high degree polynomial. In those cases Gaussian quadrature may be extremely useful. So let us now just picturize this Gauss rule to see how the weights are stacked. So you can see here, if I go from -1 to 1 in the domain X, you have the points which are located here. So this is a non-uniform grid, but it does cover the entire domain. And you can also see the weights are like this. The weight is more at 0 and they are less on the side. So this is something you'd see in many of the Gauss points and weights out there. So now we are going to use n is 7, the same integral which we have done before, and here I simply put n is 7, and now I'm going to write the Fortran code to calculate this value of I here. Let's start with the subroutine which gives me the weights and the points. So essentially these are the values. Now here, since I have 7 points, I don't want to carry scalars because that's going to give me somewhat unclean and cumbersome code. Instead, I essentially define these as vectors. So I create WGT7, XPT7, and I put double precision here. So these are all to 16 decimal places. Now this subroutine is going to give me the weight and points. Now in case you have different rules, you can at all time basically have different subroutines out there which give you the weights and points, and you can invoke the rule as you please. Now of course the function is given here. The only change is now I have to clearly define that x and f are double precision. So this is the main program. I have the main program here. Again, I have defined all the variables as double precision. And remember, you also have to define all the things which are coming out of the function. So that's something which is important. For example, if the function is named Gauss7, you can define that as double precision also. And again, I calculate the exact value and I print out Gauss7. Now the Gauss7 function is given here. Here of course you have the weights, the points, you have the 7 values of the function. So each of the values which are given from I is 1 to 7, and then I call the subroutine for weights. I calculate again b minus a by 2, b plus a by 2, and I set the value of Gauss7 to 0 because I'm going to loop through I is 1 to 7. And so I do that. I calculate whatever is inside this function here, that is BMA into XPTI, that's this term, plus BPA, that's this term. And then I basically put FNI is f of x. So essentially the function f is being called, and remember x is going in, x is this thing here which is inside this f here. So I'm going to get these here as FNI, and then I'm going to take these 7 values, I'm going to multiply each of them by the weight, corresponding weight, and then I'm also going to multiply each of them by b minus a by 2, and then I'm going to complete this do loop. So it's going to complete this do loop, and that's going to calculate the summation here. Then I'm going to end this function. Let us take a look at the output. Again, you can see the output is now extremely good, and we have basically got the value as far as definite integration is concerned to almost all the desired decimal places. Now there is going to be some difference of course in the different numbers we have obtained because I have been using a pi which is 3.14159, but the computer is generating a pi which is up to 16 decimal places. And also remember that whenever we are multiplying, dividing and taking powers and so on, what happens is that there is this numerical issue with truncation, with rounding and so on. If you are more interested in that very important topic, I'm going to leave some lectures which I have given in my optimization playlist on the end screen and description box. If I don't, please put a reminder in the comments for me to do that. Now, of course, we are not done unless we check this out with the polynomial. So we again know the important fact that as far as the Gauss quadrature rule is concerned, it's going to give me exact results for polynomials of degree 2n minus 1. So n is 7 means it's going to be 14 minus 1, that is 13 or less. So I take a polynomial of 13th degree and I put in a 14 in front so that there is a cancellation here. And so this 14x to the power 13 dx should give me 1. Let's now check it out. So what I have done is I've taken the same program. I simply changed the function here. So now I have 14 into x to the power 13. And here I have put a is 0 and b is 1. And let's now run this program. And so in this case, I get a value pretty close to 1. Again, I would have liked to see all these values as 0.99, or I would have loved to see 1.00, but somehow I'm not getting it. That may be an issue with maybe the compiler, maybe the numerical truncation, maybe round off and so on. So, but it's good enough for most problems. In fact, I would say this is certainly good enough for most engineering problems, because what happens as far as engineering problems are concerned, we don't know the accuracy of the data itself to so many decimal places. So many people in fact think that they are doing things till 16 decimal places, but what may happen is that if you are working, for example, with material properties, or you are taking something like density or viscosity or temperature, these variables themselves are not very accurate because there is uncertainty present in all those things. But then that's a different issue that doesn't have to do with the mathematics. That's something to do with random variables. So let me leave you some homework which you can do to further cement your knowledge of this method as well as programming. You can write a double precision program to implement the 10-point Legendre Gauss quadrature, and also look at the resources on the internet. There are many resources out there, for example, books on numerical programming, where you will see the Gauss quadrature being discussed in depth. It's a pretty classical area of mathematics and numerical analysis. So you will see derivations of this rule, how the different type of polynomials can be used and how the roots of the polynomials can be obtained. Maybe you have to use Newton-Raphson method for that. And fortunately, people have actually calculated the points and the weights for all these different methods. So you often can simply copy and paste these things. Now in the old days, before copy and paste came up, we had actually had to type these things very carefully. But of course nowadays you can copy and paste, but make sure that the resource from which you are copying and pasting is actually correct. So it's very important for the points and the weights to be correct. So make sure you at least compare 2-3 different sources before you are moving on with any of these Gauss quadrature rules. And also you can check, like I did with different functions, maybe you can check with different polynomials, and the method should typically work out very well. Now, of course, there is a question as to where is Gauss quadrature widely used, and you can obviously understand wherever polynomial basis functions are present, you are going to use them. So think about problems like that, wherever maybe you are solving a partial differential equation or differential equation, and you are expressing the solution in terms of polynomial basis functions. So that's going to be something which is going to be very amenable to Gauss quadrature. So before I end, I'm going to leave you with the formula for the Gauss quadrature. So essentially, if we have a definite integral of the form fy dy a to b, we can write it as a definite integral going from -1 to 1 using this transformation. And once we have done this, we can write this integral in this form here using Gauss quadrature. So essentially, if I have an integral a to b fy dy, I can solve it using this Gauss quadrature rule if I have the values of wi and I have the value of xi. Now it's quite great that, you know, even with something like 7 points, you can get very good estimates as far as most functions are concerned. So this is the power of Gauss quadrature. So what's happening here is that the points are being selected very appropriately. These are all orthogonal polynomials. So they have certain properties which essentially let you work out very well as far as definite integration is concerned. And therefore these methods require very low number of points. Now, why don't you use them all the time? Because there are many situations where you may be getting your data from certain experiments or certain sources where you do not have access to the polynomial function or to the function f. So in that case, of course, you cannot find this value at any given point. Remember, if you have, for example, x of I defined to 16 decimal places, that's not going to be very useful if you are going to do an experiment. So if you are going to do an experiment, you may be better off, for example, using values of xi such as 0 0.1, 0 0.2, 0 0.3, 0 0.4, and so on. And so in those kind of situations, a uniform grid method such as trapezoidal rule or such as Simpson rule is going to be much more useful. But in case you know the function in some mathematical form, then you can of course use Gauss quadrature. You can use those decimal numbers till 16 digits, and you can use double precision math or even more to get the different solutions out there. Now, I am going to end this numerical integration section here. If you are interested in any more videos on numerical programming using Fortran, please leave it in the comment section below so I can think about making more videos, and I will add them to this lecture. So this lecture is not going to necessarily end this series. It's going to live in the playlist. So depending on what the viewers want, I can add more content to this particular series.